Hello and welcome back. So, we are looking at using probability as a tool for analysis in data science, and in this context we started looking at the ideas in statistical learning theory. Specifically, we said that you might have some data from which you are learning an algorithm, using an algorithm learning a model, and what you can measure is the training error of this model. But what you really want to care about is the test error of the best possible model for the distribution from which the data is generated. And we said that this difference, that is the training error minus the Bayes error, can be broken down into three terms. One is the generalization error, which is the difference between the training error and the test error of the learnt model. The second is the estimation error, which is the difference between the test errors of the learnt model and the best model in the hypothesis class from which we are searching. And finally, the approximation error, which is the difference between the best model in the hypothesis class we are searching and the best model throughout, that is the Bayes classifier. And we started looking at how to bound the generalization error, that is the difference between the train error and the test error of the learnt model. And so far this is where we are. So we have managed to do the following. When you are learning from a hypothesis class which is finite, so that is, it only has a bunch of hypotheses. This is the setup in which we were looking at last time, which is called the finite hypothesis class. What we were able to prove was that the probability that the train error of the model that is learned from data, which is HS, error S of HS, remember, is the train error, minus error D of HS, the test error, that is the distributional error, right. So, what is the probability that HS makes a mistake with respect to the underlying distribution D? This difference is greater than or equal to epsilon, is less than or equal to, specifically we proved that this is less than or equal to the cardinality of h times e to the minus 2n epsilon squared, and because of this, what we could infer from this is that if n, which is the number of samples, so the more the number of samples, the better our difference between the train and the test error is going to be. That is, the train error is a good proxy for the test error. So, if n is greater than or equal to something like, let me use the same color, 1 by 2 epsilon squared log of h by delta, then the above probability is less than or equal to delta. That is, if you fix epsilon and delta, then one can precisely say how many samples do we need so that we can be 100% or not, like 1 minus delta percent confident that my train error and the test error are going to be at most epsilon away, right. So, that is what we proved last time, and which is good, which is great, right. So, which means that if you have a finite hypothesis class, we will definitely generalize. That is what this means, right. So, remember, this does not tell about goodness of the algorithm itself. This just says that no matter which hypothesis our algorithm picks, its train error and test error are going to be close to each other. That is what this is basically saying, right. So, this is not a statement about a specific algorithm. This is a statement about the hypothesis class itself, and this is what was called as a uniform convergence argument, and that is because we are saying that not just the hypothesis that our algorithm picks has close training and test error, but then every hypothesis that you could have picked has close training and test error, and so our algorithm's particular choice will also have this property, right. So, that is the uniform convergence argument which we saw last time. So, the question that we want to ask today is what happens when cardinality of H is infinity, and this is the more practical setup, because we will never learn in machine learning from a finite hypothesis class, right. So it's not like you only have, let's say if you're learning a linear classifier, you only have a bunch of 100 W's and then you have to pick one of these 100 W's. That's never going to happen, right. So we are always learning from an infinite hypothesis class. For example, this could be linear hypothesis class, which is just the set of all linear classifiers, or this could be the quadratic hypothesis class, right, which is all quadratic functions of the sign of quadratic function of the input is the greater than or equal, determines the output, right. So like how sign of W transpose X will determine whether it's a +1 or -1, our prediction. Similarly, in a quadratic hypothesis class, if I pick one classifier, it's going to do like a sign of some quadratic function of the input, X, right. So it's not W transpose X, it will be some quadratic function, which means that all the square terms of the features will be involved, and all the cross terms will also be involved. And now that would be your quadratic hypothesis class. Of course, there are infinite such possibilities there, because even for linear we have infinite such possibilities. So so first thing is that first observation is our H less than infinity argument breaks down, right. So if that already works for H equals infinity, then we don't have to prove anything new, but then this argument breaks down, because what we are essentially saying is that the right hand side is the probability, the chance that train error and test error is away, is far apart by at least epsilon, is at most cardinality of H times e to the -2n epsilon squared. But then if cardinality of H is infinity, then it doesn't make sense. This probability is less than or equal to infinity is a useless statement to make anyway, right. So that argument is going to break down. So we need some other way to argue what happens when you have an infinite hypothesis class. And the key insight for this is the following. So let's say we have some training sample, given a sample, let's call this S, x1 to xn. Of course, yi is all 0, 1, y is the label space, that's in 0, 1. Now we are labeling each data point as 0 or 1, and then there are n such data points, right. So which means that if you ask how many possible labelings are there for this set of n points, right. So if there are n points, these could be any n points, but then the labels can be either 0 or 1. So each data point can have either 0 or 1 as its labels, and then n of them. So how many possible labelings can we have? So we can have at most 2 to the n labelings, right. So this is to say that this is because each data point can have 2 labels, and then there are n of them, 2 into 2 n times, so that is 2 power n labelings. So now what does this mean? This means that let's say we have our hypothesis class as the set of all possible classifiers. That is set, every classifier is a function from, let's say, Rd to 0 or 1, and we have every possible function. Now even if you have every possible function, right, so what I can do is, I don't know which is the best one or anything of that sort at this point, but then I can take each one of these and try to label my n data points, because the data set size is finite, it's fixed, right. So that's what is given to me, and then there are n of them, and now if I try to label it, I can get only a finite set of labels, and that is at most 2 power n. In fact, if you have the set of all possible classifiers, then yes, there is one classifier which is going to label all these endpoints as 1, there will be one classifier which will label all these endpoints as 0, and one classifier which will correspond to, there is at least one classifier corresponding to each of these bit patterns, right. So, 2 power n bit patterns, which means that now the number of h itself is infinity. The key point is that h is infinity because it is a set of all possible classifiers, right. So, and there are infinite classifiers. Even if it is linear, there can be infinite classifiers. This is the set of all possible classifiers, which includes linear, quadratic and whatnot. So, there are going to be infinite such classifiers. H is infinity, but then the labelings is only finite, 2 power n, right. So, which means that if you think of this bag of classifier bag, right. So, this is the hypothesis class. What essentially we are saying is that there are these equivalent hypotheses in this bag, right. Right. So, maybe this is the one that corresponds to the one that predicts 0 for all the n data points, and this is the one that might predict 1, right. So, this region, right. So, each point in this region corresponds to a classifier, and every classifier in this region, I mean, when I say region, I am loosely talking about it. So, all I am saying is that there is a set of classifiers which are going to say predict all ones for all the data points. There is a whole set of classifiers which are going to say all zeros, and for the purposes of for our purposes, all of these are the same because they have, they make the same training error, for instance, right. So, because no matter which classifier I pick from this region, if their labelings for our set of data points, training data is the same, then the training error is going to be the same. So, effectively they have the same effect on at least one of these quantities that we are interested in, which is errors of h's, right. So, the training error is going to be the same. So, so this is the key intuition that effectively there can only be finite number of classifiers, right. So, though we are calling the hypothesis space as infinite, the effective number of classifiers is only going to be finite, which is equivalent to the number of distinct labelings that we can achieve for our training set in this case, right. So, so let us say if we learnt then from a set of all possible classifiers, then again, so this whole discussion I am not going to get too precise, I will give you a very high level intuitive view only. So, let us say our cardinality of h is not then infinity, but then only effective cardinality, which means that we might get something of this form, right. So, rs of hs minus rd of hs is greater than or equal to epsilon is less than cardinality of h, which is 2 power n times e power minus 2 n epsilon squared. So, now this is still okay, at least better than saying cardinality of h is infinity, which is a useless bound. But now we can ask what happens to this product, right. So, as I get more and more samples, right. So, in the previous case, because this was a fixed number, let us say I had only a finite set of hypotheses, let us say 1000 hypotheses. So, this would be something like 1000 times e power minus 2 n epsilon squared, which means that as n goes to infinity, as I get more and more samples, this 1000 is a fixed number, it is not going to affect the asymptotics, whereas this value goes to 0 as n goes to infinity, which means that my train error becomes closer and closer to the test error, and so I can make them arbitrarily close how much ever I want with whatever probability, right. So, that was the idea. For large enough n, I have that property. But now here what this is saying is that both these terms depend on n. If I increase the number of data points, then the number of potential labelings also increases, it becomes 2 power n, right. So, if n becomes n plus 1, this becomes 2 power n plus 1. So, this exponentially grows with respect to n, this exponentially decays with respect to n, and so these effects kind of cancel out. So, if as n goes to infinity, this product does not go to 0, right. So, this does not go to 0 as n goes to infinity for a fixed epsilon. So, because of that, what this essentially is telling us is that now if I learn from the set of all possible classifiers, then intuitively I should not expect all these classifiers to generalize, right. So what might happen is, I mean, in a different way you can say that I might end up memorizing my training data or overfitting my training data, and so I may not be able to generalize. The training error and the test error may not be, the training error may not reflect the test error, right. So there is no structural assumptions that we are making because we are learning from the entire set of all classifiers, and so I will always be able to get zero training error, because there will be some classifier, and then let us say if I am trying to find the classifier which makes the least error, then there will be some classifier, forgetting the computational aspects of it. For the moment, if we are trying to find a classifier which makes least training error, and let us say we are able to do that, so then I will always be able to get that classifier which will which would have memorized data. In fact, if I know that I am learning from all possible classifier, there will be a classifier which will give me the exact y for every x, right. So the training error, I mean, I can always find a classifier with zero training error, but I do not know about its test error necessarily, right. So because from what we are saying is that, because there are too many classifiers, I will not be able to get a uniform convergence. I will not be able to say that all these classifiers are going to have close training and test error, right. So our line of attack was the following: we do not know which one our algorithm will pick. So we want to prove for every classifier that is there in the space of classifiers. Now if there are infinite classifiers, we are saying, well, though there are infinite, there are only finite, effectively finite ones, but then there are too many finite ones that I will not be able to prove anything useful if I am learning from the set of all possible classifiers, because this product won't go to 0, right. So this is just an argument to say that I should not be learning from the set of all possible classifiers. So then one asks, then what should I do, right. So then this is also kind of suggesting that we should restrict the capacity of the hypothesis class, right. So we should learn from a structured hypothesis class, linear hypothesis or quadratic hypothesis, whatever it is. We should learn, hopefully that won't have this problem. We do not know yet, but hopefully if you restrict the hypothesis class, then perhaps we might be better off. But will that happen, right. So if I restrict the hypothesis class, say that I do not allow for all possible classifiers, but only for certain types of classifiers, then does that mean that the set of all labelings that I will end up getting is restricted, right. So that is the question that we want to ask, and let us see where that takes us, right. So just to get a sense of what I am talking about, let us look at a following example. Right. So in this is a very simple example. In this case, our domain, the data comes from just real numbers R. Usually it is RD, but then now I am just going to say that it is just one feature, the X is just R, and let's have, as usual, Y is 0, 1. The label is 0, 1, and I am going to define my hypothesis class H, and I am going to call this HINT. INT standing for intervals, and the way I am going to define it is as follows. So what are the classifiers that I am allowing? Well, every classifier in my bag, HINT bag, is of the form HAB, right. So every classifier has a and a B. These are two real numbers, and what does this mean? So this is the set of all HAB such that HAB of X will be plus 1 if A less than or equal to X less than or equal to B and 0 otherwise. So this is my set of all classifiers, right. So for example, there might be a classifier which is H3 7.5. Right. So let us call this, let me put a comma to indicate these are two different numbers, H3 7.5. What is H3 7.5? Well, on the real line, so this is the real line minus infinity to infinity, so there is the value 3 somewhere and then the value 7.5 somewhere, and now if my input data point is in this range, in this interval, this classifier H3 7.5 will say plus 1. If it is less than 3 or greater than 7.5, this is going to say 0. That is, it is kind of an indicator classifier of the interval 3, 7.5. Now, there might be one more classifier which is 3 comma or 3.1 comma 7.4, right. So, 3.001 comma 7.499, that might be a different classifier, right. So, which will have something similar, but the interval is almost similar 001, this is 7.499, and then it is going to be plus 1 here and 0 elsewhere. So, as you can see, right. So, for every choice of A and B where A is less than or less than B, this classifier there is a classifier, and because A and B can be any pair of numbers, there are infinite of them. So, this H, the size of H int, the interval hypothesis class, is infinity. So, this is the first point, right. So, we might want to study this, right. So, what is what is the question that we are interested in? Well, does it, we know that this has infinite classifiers in this hypothesis bag, but given a set of data points, how many potential labelings can classifiers from this bag realize? That is the question that we are asking. So, because we want to know, is it 2 power n, right. So, I have now made a restriction, I am not allowing the set of all classifiers, right. So, the set of all classifiers would have been something like any H from R to 0 comma 1, that would be the set of all classifiers, right. So, if my H has all H such that H is from R to 0 comma 1, then that is the set of all possible classifiers, which I know that if you give me n points, I will get 2 power n labelings. But now I am restricting it, I am saying that these are, I am only allowing interval classifiers, and now I am asking the same question, if I take a bunch of points, how many possible labelings can this hypothesis class achieve on the set of points that I care about, right. So, let's see how many, let's take an example, right. So, say my data set S was just the for a bunch of 4 points, let us say -1, 2, 3.5, 7.5. I am just cooking up these numbers, right. So, let us say these are the 4 numbers, which means that my data set looks like the following. This is the real line. Now, think of this as the training set, for instance, right. So, I have -1, I have 2, I have 3.5, and I have 7.5. Now, the question that we are asking is, I can take every interval classifier in my hypothesis bag, there are infinite of them, and then use that to classify these 4 points. So, that would give me a set of labels, 4 labels, 0 or 1 for each of these points, right. Now, I am asking how many such distinct labels can I achieve with this bag that I have, right. So let's look at it this way, right. So, for instance, I can draw an interval like this. Let us say this is my A and this is my B, right. So, if this is my interval, so then what is the labels for these 4 points? Well, this interval, obviously all the 4 points are within this interval. So, all the 4 points get +1 label. So, the +1, +1, +1, +1 is a bit pattern or label pattern that is achievable using this hypothesis class. What else is achievable, right? So, now I can, instead of putting this interval here, I can put it in different places. So, before I do that, I mean, this may be a good time to pause and think about it, and you figure out yourself how many possible labelings are there, and then I will explain it now. Okay, so let's go ahead and see how many are there. So, instead of putting the right hand side bracket here, let's say if I had put the right hand side bracket here, maybe I'll use a different color. Oops, okay. So, let's say if I had put the right hand side bracket here, the left hand side bracket can be here itself. So, let's say this is A prime, B prime. Now, what are the labels that I get? I get +1, +1, +1, but then this B prime is before 7.5. So, this guy gets 0. Yeah. So, now you can see where this goes. So, I can push this forward here and I will get one more labeling. If I put it here, I will get one more labeling. if I put it here, I will get one more labeling, right. So, for a fixed A which is to the left of plus 1, I have 5 different choices for the right hand side, the right end of that interval, right. So, again it does not matter, for example, if I put it here or if I put it here, it does not matter, because for both of these the labeling is going to be plus 1 plus 1 0 0, right. So, for this and this, right. So, which means that no matter where I put the right hand side point in this interval between 2 and 3.5, I am going to get the same labeling. That is why, though the number of classifiers might be infinite, the number of labelings becomes finite. So, now let's try to calculate how many will I get, right. So, if I fix the left hand side, again if I fix the left hand side to be before plus 1, right. So, this is sorry, minus 1. I mean, does not matter what these numbers are really, right. So, these are just 4 numbers which are arranged in increasing order. If I fix it here, then I have 5 choices, right. So, here, so in this interval, this interval, this interval, this interval and this interval. Of course, the right end of should be greater than the left end. So, there are only 5 choices. Now, instead if I fixed somewhere here, now the left interval is here, which means that minus 1, no matter for which classifier wherever I put the right interval, minus 1 is going to be labeled as 0, because it is to the left of this. But then for the other points I have other choices, because now I have one choice to put here, put here and put here, right. So, remember all these labelings are going to be different from the light blue labelings, because for the light blue minus 1 was always plus 1, right. So, except for when I put it here, in which case all of them will be 0, right. So, otherwise minus 1 was always plus 1, right. So, now how many options do I have? I have 1, 2, 3, 4, right. So, this is going to be 4, 1 is reduced. Now, I can go forward and then say I will put it here and then ask how many labelings I will get. That will be 3, if I put it here I will get 2, if I put it here outside this, well then that is going to be the same as this guy. So, because I mean wherever the right hand side is, all of these are going to be labeled as 0. So, that is same as saying this combination. So, that is a repeat thing, right. So, basically what we are getting is that depending on the number of points, right. So, we might get something like n plus 1 plus n minus 1 plus dot 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 plus 1. Right. So, in other words, we will get something like order of n squared. So, because this sum is order of n squared, right. So, n squared possible labelings only out of 2 power n possible labelings. That is the interesting part, right. So, if I had n data points, I could potentially get 2 power n labelings, but then because I have restricted the hypothesis class to be of the form interval classifiers, I am only getting n squared labelings, right. And the question is that a good thing or a bad thing, right. So, yes, the number of classifiers has reduced. So, this is the effective number of classifiers. So, how does that help us? Well, if I know why are we doing this, right. So, if I know the effective number of classifiers, then I can convert this into a bound of the following form, RS of HS minus RD of HS, whichever my algorithm picks out of these interval classifiers. I do not know, that depends on my algorithm, but I know that because there are only n squared classifiers, this is at most n squared times e power minus 2 n epsilon squared, right. So, again, so earlier remember this was 2 power n, now it is just n squared. Of course, this increases with n and this decreases with n, but the good thing is the increasing part increases only at a polynomial rate, it is only at rate of n squared, whereas the decreasing part decreases at an exponential rate, right. So, which means this product is going to keep decreasing as n becomes larger and larger, right. So, in other words, we do not have enough to compensate the amount of decrease, and it is only n squared, but then it is decreasing as e to the minus 2 n epsilon squared, right. So, that is a much faster decrease than how much this increase can tackle, and that is a good thing, because this will go to 0 as n goes to infinity. So which means that we have our kind of first result that if I restrict my classifiers to be a set of interval classifiers, then though there are infinite such classifiers, I will still have effectively only order of n squared classifiers, and so I will be able to prove uniform convergence. Again, so there are some subtleties here which I will probably reserve for a full-fledged course on statistical learning theory. So yes, so if you pick two classifiers which have the same labeling on n points, they will have the same training error, right. So they don't, you cannot distinguish this value between those two classifiers. Whereas, but then this value is not necessarily the same, right. So if you have two classifiers with the same training error, their test error need not be the same. So you will have to do slightly more, I mean, so you will have to do something called as a symmetrization trick to actually prove this, but let us not do that proof in this course. It suffices to say that what really matters is how many effective classifiers are there, right. So and that's the thing, that's the term that's going to appear here, and that's what will determine whether we have uniform convergence or not, right. So yes, so in this case we do have uniform convergence, and so our generalization error will go to 0 as n becomes larger and larger, which is the good thing, right. So that's what we wanted. So that's the first point. Now of course we are, this is a toy example in some sense, right. So we had only one feature, and our classifiers were just the interval classifiers, right. So we are never going to learn an interval classifier on just one feature. I mean, that's practical, that's not the practical problem that we are interested in. The practical problems we are interested in is in linear classifiers, quadratic classifiers, things like that. So but then this gives us like a good way forward in the sense that we at least know that there are these hypothesis classes where you don't necessarily get all possible labelings. The structure restricts the possible labelings. The possible labelings is, if it is polynomial in n, then you get uniform convergence. Now how can I, so this is one way to argue that you have n squared labels, right. So is there a way we can somehow associate how complicated a hypothesis class is, right. So in other words, so intuitively now we have looked at two different hypothesis class. One is the hypothesis class with set of all possible hypotheses. The other is this one, which is the interval hypothesis class. Now when you have all possible hypotheses, no matter how many data points you give me, I will get 2 power n labels, right. So that is one extreme. The other is that's a much complicated hypothesis class, whereas this one has structure. So this is not as complex as that one, right. So the question then is that, is there a natural way to define a complexity measure for a hypothesis class? If I tell you, hey, this is the hypothesis class from which I am going to learn, then is there a way to say that will uniform convergence hold or not in this hypothesis class, right. So so that will lead us to one of the most interesting and the most important cornerstone of modern statistical learning theory, which is to measure complexity of hypothesis classes.